Here's a question for you. But before I show it, I want you to clear your mind of all distractions, because I want you to answer out loud as quickly as possible. Then we're going to reflect on what the process felt like. You ready? Don't worry, it's an easy question. And go. Okay, so 25. And how did you get there? Well, if you're like most people, your brain calculated the answer in one of a couple of ways. So maybe you thought, I know 7 and 8 make 15, add the 10 on, you've got 25. If you're more like me, then what happens is something like this. You're on 17, you know 3 gets you to 20, I need an extra 5 because I'm adding 8 altogether, so that gets me 25. Our brains like to do this because we like multiples of 10. Now, you might have done it a different way, and that's fine, but if you have any arithmetic fluency, you're familiar with the idea that we can break sums down and rebuild them in ways to make them easier. Many people looking at this would do it the easy way and pair 8 with 2 and 9 with 1, 2 10s make 20. But let's just consider what we've had to assume in order to do that breaking and rebuilding. So if you did this the 7 and 8 make 15 way, you've said 17, which by the way is 10 plus 7, and then add 8, that's the same thing as if you add 10 to the total of 7 plus 8. You've assumed that you can do this second calculation first and still get the same answer. And likewise, if you did it the way I like to do these, the plus 3 plus 5 way, then you've said 17 plus 8, 8 by the way is 3 plus 5, is the same thing as if I do 17 plus 3 and then add the 5. Again, you've assumed that you can do this calculation first and still get the same answer. And here, if we want to do this the easy way and do 8 plus 2 and 9 plus 1, we've assumed that we can swap the order entirely and still get the same answer. Addition seems to play nice in this way, but why? Can we prove that it always will? And what does it even mean to add? If you've seen my previous videos, you know these numbers are actually encoding sets. How do I take something like the 3 set and combine it with the 2 set in such a way that it produces the 5 set? I must admit, the advent of the advantageous explanation I advocate and will adeptly adopt while advancing our knowledge will require an adjustment and adaptation of our thinking. Adhere to my advice and join my admission-free adventure advertising mathematics' most admirable, adorable, addictive and other adjectives. An adequate introduction? It's about how to add. First, let me talk about the sweetest thing there is, definitions. Now, if that's not your sort of thing, then I'm sorry. Not for my content, but for your disposition. I mean, who doesn't love definitions? Anyway, for the 3 people who are still with me, hi. I sometimes find that there's a chicken and egg problem with definitions. Often when we're learning, we learn a definition and then we explore the properties. But often, we want a thing to exist that has those properties and we define it in that way. When we constructed the 3 set as the successor of 2, it wasn't just a happy coincidence that it happened to contain 3 sets. No, we deliberately constructed it that way so that it aligns with our intuition. All of this is to say, how do we want addition to be defined? Well, we want it to agree with our intuition that it's the total count of 2 collections of things. Now, I could just tell you the definition of addition, but to be honest, it's quite clunky and inelegant until you wrap your head around it. Instead, let's build the definition of addition together, building it in the way that we want addition to look. Definition of addition. Definition of addition. That's never going to sound right. Now, this video is intended as the 3rd part in a series of building mathematics from the ground up. So if you haven't seen my videos on numbers and counting, I recommend that you do so, but don't worry if you haven't, I'm going to go over the key points now. So a quick reminder of our foundation. We have these axioms, pairing, subsets, union, and extensionality, and we can use those to construct sets. And back in my first video, I also had this, the concept of a successor. Now, this isn't an axiom, rather it's the application of the axioms to go from one set to its successor set. Now, as much as I love these sets, the time has come to streamline them a little bit. So remember how I called the empty set 0? Let's rename the empty set 0 in each of these. And 1, that's the set containing 0. So anytime we see the set containing 0, we can rename it as 1. And 2 is the set containing 0 and 1. So wherever I see the set containing 0 and 1, I can relabel that as 2. And hopefully you can see the pattern here. 0 is 0, 1 is the set containing 0, 2 is the set containing 0 and 1, 3 is the set containing 0, 1 and 2, and so on. If we keep taking the successive, we can generate any natural number. In general, the natural number n is the set containing the numbers from 0 to n minus 1. So let's think about our overall objective. So we would like a definition of addition to be such that we take two numbers and output another number, and that output number we want to align with our intuition. Let's look at a concrete example of 2 and 3. We want to take 2, the set containing 0 and 1, 3, the set containing 0, 1 and 2, and output 5, the set containing 0, 1, 2, 3, and 4. Now I'm going to show you one way that we might go about this, but it's going to be kind of bad and not the real definition of addition that we're going to use. I'm just going to show you this to explore the malleability of definitions, because we sometimes think of mathematics as something that's already done and finished and just there for us to learn. But mathematics isn't like that. It's an ongoing process. Some say a process of discovery, some say a process of invention. Others are like me and sit somewhere in between. In any case, it requires work to figure out, and by exploring multiple avenues, we get a feel for what we want to get out of mathematics. So we might say this: combine the 2 set and the 3 sets together into a single set, and then see which natural number is in bijective correspondence with that amalgam. Well, the first problem with that is this: how am I doing the combining? Because if I just union these 2 sets together, then because I discount duplicate members, this whole thing is actually just the set containing 0, 1, and 2, and that will be in bijective correspondence with 3, and we don't want that. So we could just bodge it though, right? Because what we could do is we could use the ordered pairs that we set up in the last video and tag all the elements of the 2 set with some element A, and tag all the elements of the 3 set with some element B. And here A and B are just 2 elements that we've constructed that are not equal to each other, and neither of them are equal to any of the numbers here, so these are really 5 distinct elements. And then we test to see which natural number is in bijective correspondence. So we can see that if we pick a number less than 5, we're not going to be able to make a surjection. Just like if we choose a number greater than 5, we're not going to make an injection. Only with 5 will we get a perfect bijection. Now, I think this could work, but there's some funny business going on with this whole test which number is in bijective correspondence idea. I mean, what if I did this with 2 massive numbers? Would I have to sit there all day testing numbers to find the one that happens to be in bijective correspondence? Well, the way we've set it up, yeah. What we actually want is something a bit more like my ideal date night. We want to follow a structured process. We want something that automatically outputs the answer, not just checks until we find the answer. I think we mathematicians would quickly lose credibility if our solutions to problems basically just came down to the answer is to check until you find the answer. Although, for those of you who've read my PhD thesis, you know that that's basically what I did for 4 years. I'm just kidding. Of course you haven't read it. Nobody ever will. And I'm okay with that. But I wanted to show you this to illustrate that constructing definitions is difficult, with all sorts of edge cases and places where we need to be really careful with being watertight. So with that in mind, let's think about addition. What do we know about it, and what do we want it to look like? I told you not to touch my things! Sorry about that. So let's start with the basics. Let's start with the first number, 0. How do we add 0? Well, intuition tells us that adding 0 doesn't change the number. So let's just define addition in that way. So if I take a general number n, let's define n plus 0 to just be n. Okay, that's a good start. So what about the next number? What about adding 1? Well, when you think about it, adding 1 just means go to the next number. So 2 plus 1 is 3, the number after 2. But hang on a minute, we've seen that idea before. The successor, that's how we define the numbers. The successor of 2 is 3, 2 plus 1. The successor of 3 is 4, 3 plus 1, and so on. So let's just define it that way. n plus 1 will be defined to be the successor of n. Here I'm using the notation S of n to denote the successor of n. But let's think about adding 2. I already know how to add 1, so surely adding 2 is a matter of doing add 1 and then doing add 1 again. Great, now I know how to add 2. So let's think about adding 3. Well, I know how to add 2, and then I can just do add 1 to complete the addition. So great, now I know how to add 3. Now let's think about adding 4. Well, let's do add 3 and then do add 1 to complete it, and so on. And hopefully you see where this is going. Adding a general number k will be a matter of adding the number before k, doing the previous addition, and then adding 1 to complete it. It's called a recursive definition. So I've written it down like this. N plus a general number k is defined to be n plus the predecessor of k, and then add 1 at the end to complete the calculation. The only problem with this is I haven't really talked about the predecessor of k. We know how to take the successor. It's a sequence of application of those axioms, but how do I get my hands on the predecessor? Well, luckily we don't really need to worry about it because there's a neat trick that we can use to rewrite this in terms of the successor. So think about this. This definition is based around k. So if I want to know how to add 12, for example, I put k equal to 12, and then I have n plus 12 is defined to be n plus the predecessor of 12 plus 1. But k is arbitrary here. You know, I could have used any symbol. So the symbol I'm going to choose is the symbol k plus 1. You'll see what I mean in a minute. Hopefully you can see so far I haven't actually changed this definition at all. I'm just illustrating that I could have chosen any letter or any symbol to put into this definition and it would still work. The choice of k is arbitrary. So like I said, I'm going to choose k plus 1 and we'll see what happens. Now I know what you're thinking, why on earth have you taken something that looks quite neat and made it even more complicated? Well, the reason is we can actually tidy this up in a really nice way. So think about what k plus 1 actually is. We know how to add 1. It means take the successor. So I can rewrite this as the successor of k. Now let's think about this, the predecessor of k plus 1. So imagine you've got a number k, then you've added 1, and then you've taken the predecessor, the number before k plus 1. But that must just be k, right? So this whole thing here is k, and I'm adding 1 to this sum, and I know how to add 1, it's to take the successor. So all in all, we have this. N plus the successor of k is defined to be the successor of n plus k. And that's that clunky definition that I referred to earlier. When I first saw this, I didn't really get what it was saying. Why have we defined addition in this really convoluted way? N plus the number after k is equal to the number after n plus k. But I promise you that once you see an example, this whole thing is going to make sense. So let's look at an example. Let's look at 2 plus 3. Well, let's think about what 3 actually is. It's defined to be the successor of 2. But now I can use this part of the definition. Whenever I have something of the form n plus the successor of k, I can rewrite it as the successor of n plus k. So let's do that. I've got something in that form here. And notice what we've done here. We've started with 2 plus 3. We don't know what the answer is, we're trying to work it out. But we now know that we just need to find out what 2 plus 2 is, and then take the successor. We know how to take the successor. So the 2 plus 3 problem has boiled down into the 2 plus 2 problem, and we can keep going. So this is the successor of 2 plus 2, that's the successor of 1. So let's rewrite it here and focus on this thing here. This is of the form n plus the successor of k, which I can rewrite as the successor of n plus k. So 2 plus the successor of 1 is the successor of 2 plus 1. And again, just appreciate what we've done here. We started with 2 plus 3, and then we boiled it down into find what 2 plus 1 is, and then take the successor twice. But I know how to add 1. 2 plus 1 is defined to be the successor of 2. So the answer to 2 plus 3 is the successor of the successor of the successor of 2. It means find the successor of 2 3 times. And when you think about addition, that's what it really means. You know, if you want to add 7, you're going to go up by 7. You're going to add 1 7 times. And you can imagine doing this with a really big number there. You know, imagine a really huge number like 17 or something like that. 2 plus 17, that will be the successor of 2 plus 16, which is the successor of the successor of 2 plus 15. And you'll keep going, and eventually it'll boil down to taking the successor of 2 17 times. I just love it. And hopefully you agree it's deserving of its own brick. But what about the properties of addition that we know and love? Does this definition of addition guarantee that we can break apart and rebuild sums like we did our earlier examples? Yes, but don't take my word for it, let's prove it. Now, proving these addition properties is a surprisingly difficult task, and we're going to need some higher level mathematical machinery in order to get there, but stick with me on this journey because it will be worth it, I promise. We're going to need the inductive principle, and fair warning, this is a topic that's notoriously misunderstood by non-mathematicians, and I'd say even by some mathematicians, but once it clicks, it clicks like nothing else. I should also say that mathematical induction is not related to inductive reasoning, which tends to be forbidden in mathematics in favour of deductive reasoning, but that's a topic for another time. The difference between deductive, inductive and abductive reasoning. Would that make a good video? Let me know in the comments. Please excuse the crudity of this model, I didn't have time to build it to scale or to paint it. So let's say I have an infinite line of people, so this line goes on forever, and let's say I want to start a Mexican wave. You know, like you see in stadiums where people wave one after another and it creates that nice wave effect. Now the way I'm going to do that is I'm going to program these humans with the following rule. Whoever you are, if the previous person waves, then you will wave. So person 3 is thinking, I don't know if person 2 is going to wave, but if they do, then I will wave. And person 4 thinks, I don't know if person 3 is going to wave, but if they do, then I will wave, and so on down the line. Then we program human 1 to wave, and then let's see what happens. So person 1 is going to wave, and then person 2 thinks, the person before me is waving, therefore I must wave. So then person 2 waves, and then person 3 thinks the person previous to me is waving, so I must wave, and so on down the line. And hopefully you can see that eventually everybody in this infinite line of people will eventually wave. Now the natural question to ask next is, what the hell are you talking about? Well, let's say I have a statement about numbers, and I want to prove that it's true for every number. Let's say it's like a rule or a formula that works for every single number. But I don't want to sit there and write an infinite list of proofs proving that it's true for every number. What I can do is I can use this shortcut. Let's say that I show that if it's true for one number, then it's true for the next number. So I don't know if it's true for any of the numbers, but I just know that if it is, then it's automatically true for the next. And then I prove it's true for the first number. So with these two facts, the fact that it's true for the first number, and the fact that if it's true for one number, it's true for the next, well then, let's see what happens. It's true for 1, which means it's true for the next number, which means it's true for 2. But if it's true for 2, it's true for the next number, which means it's true for 3, and so on. And just like this Mexican wave, we have an infinite list of proofs. So that's proof by induction. You prove that if it's true for one number, then it's true for the next, and you prove that it's true for the first number, thereby proving that it's true for all natural numbers. Now, before we move on, I want to give you an example of the inductive process. Many of you have probably seen this before. This is like proof by induction 101, but I really want to anchor the concept for those who've never seen this before. So we're going to relax our axioms and sets and everything like that and deal with numbers colloquially. So you've probably seen these before, the triangular numbers, 1, 3, 6, 10, 15, etc. The way we get from term to term is to add the position of the next term. So to get to position 2, I add 2. To get to position 3, I add 3, and so on. What if I asked you, what is the 100th triangular number? Well, you could sit there with your calculator and you could do 1 plus 2 plus 3 plus 4 plus 5, etc. until you get to the 100th term. But that would take a long time. What you could do is use the shortcut. If you take the number 100 and then times it by the next number, 101, and then divide the answer by 2, you'll get 5050. and that is the 100th triangular number. Why does that formula work? Well, let's prove that it works by induction. So we're going to prove this formula here by induction, that the nth triangular number is given by n times n plus 1 all divided by 2. And we're going to do that by induction. And to do it by induction, we need to say, hypothetically, if the formula works for one number, then it automatically works for the next number. So if it is the case that the kth triangular number is k times k plus 1 over 2, then what is the number in position k plus 1? Well, we get there by adding k plus 1 to the kth triangular number. So let's do that. So we've added k plus 1 to our kth triangular number, and through some algebraic manipulation, we get to the following. And I'm not going to go through all the details here. You can do that in your own time. And we get to this. And this is k plus 1 times the next number all divided by 2. So just to reiterate what we've done here, we've said if the triangular number formula works for one number, then it automatically works for the next number. We don't know if it does work for any number, but we're just saying that if it does, then it works for the next. Now, does the formula correctly predict the first triangular number? Well, the first triangular number is 1, and if I put n equals 1 into this formula, then I get 1 times 2 all divided by 2. And 1 times 2 is 2, divided by 2 is 1. So it correctly works for the triangular number in the first position. But if it's true for one number, it's automatically true for the next. And if it's true for that number, it's automatically true for the next, and so on. So this formula does indeed work for every natural number. Phew. Okay, deep breath. Back to the land of our axioms and sets and all that good stuff. First, let's look at this notion, that I can add the numbers in any order, i.e. that if a, b, and c are numbers, then a plus b plus c, that's the same as a plus b plus c. It has a special name, we call it associativity. And intuitively, it makes sense, right? If I want to count how many objects I have in these three collections, it doesn't matter if I count these two collections and then add this to the total, or count these two collections and then add this to the total. But this is something that we can prove inductively using our concrete definition of addition. Okay, there's a lot going on here, so just bear with me. I want you to think of a and b as fixed numbers with a fixed sum, a plus b, and we're going to say if k is a number that plays associatively with a and b, then we'll prove that the next number automatically plays nicely with a and b. So we're going to say if k happens to be associative with a and b, then k plus 1 will be associative with a and b. That's what we're going to prove. So look at this, a plus b plus k plus 1. We want to show that k plus 1 behaves associatively with a and b, and that means we need to show that if we do b plus k plus 1 and then add a, it's the same answer as if we add a and b first and then add k plus 1. So what do we know about k plus 1? Well, we know how to add 1. That just means to take the successor. So let's rewrite it in that way. So we have a plus b plus the successor of k. And now the definition of addition tells us that if we have one thing plus the successor of the second thing, that's the successor of the first thing plus the second thing. So let's apply that definition here. But we've done all this under the assumption that k plays nicely with a and b. So k is associative with a and b, so let's use that and rewrite this. And now the addition definition tells us if we have the successor of one thing plus the second thing, it's the first thing plus the successor of the second thing. So let's rewrite this again. And finally, we have again the successor of two things added together. So the addition definition tells us it's the first thing plus the successor of the second thing. So finally, the successor of k by the addition definition is k plus 1. And hopefully you noticed that's exactly what we set out to prove. Look, we've got k plus 1 added to the sum of a and b, equaling the result of adding it to b and then adding a. So what we've done is we've shown that if k plays nicely, if some number plays nicely with a and b, it's associative, then the next number automatically plays nicely. We don't know if any numbers do play nicely. We just know that if one does, then the next does. But now we will show that 1 plays nicely. Let's do that. So down here I've got a plus b plus 1. I need to show that this is the same as b plus 1 and then add a. Well, we know how to add 1. That's just the successor of A and B. And then applying the addition definition, the successor of the first thing plus the second thing is the first thing plus the successor of the second thing, but the successor of B is just B plus 1 as required. So we've shown that 1 is associative with A and B, and we showed that if a number is associative, then the next number is associative. So therefore, all numbers are associative with A and B. And what's more, we never specified what A and B are. This will apply with any two numbers A and B. So we can make those whatever we want. So that means that any three numbers will behave associatively. They'll have that associative property. Let's look at this property of addition now, the idea that I can reverse the order in which I'm adding the numbers. So in general, for numbers A and B, A plus B is equal to B plus A. And again, this should make intuitive sense, right? So if I'm trying to find the total count of the collection here, then I can add these and then followed by these, and I should get the same answer if I add these and add these. This property is known as commutativity, or the idea that A and B commute if we can swap the order and still get the same answer. Now this proof is a little more difficult than the proof for associativity. We're actually going to do it in two stages, two proofs by induction, because as that kitchen hob salesman once told me, why settle for one induction when you can have two? We're first going to prove this, the weaker version of commutativity that states that 1 commutes with any number. So given any number A plus 1 is the same as 1 plus A. That's going to be our first proof. So let's start our induction. Let's say if k commutes with 1, then we will demonstrate that k plus 1 must also commute with 1. So again, if we're in that hypothetical scenario where we have a number that commutes with 1, we will show that that automatically implies that the next number commutes with 1. So let's see what happens. K plus 1 plus 1, but remember, this is all assuming that 1 commutes with k. So I can immediately rewrite this as 1 plus k plus 1. And now, since we know that addition is associative, let's go ahead and use that. 1 plus k plus 1 is the same as 1 plus k plus 1. And there we have it. We've shown that if a number commutes with 1, then the next number commutes with 1. Now all we need to show is that 1 commutes with 1. But actually, that's pretty straightforward because 1 plus 1 is in fact identical to 1 plus 1. So if I swap the orders of 1 and 1, I get the exact same thing. So trivially, 1 commutes with 1, and we said that if 1 commutes with 1, then 2 commutes with 1, if 2 commutes with 1, then 3 commutes with 1, and so on forever. So 1 does indeed commute with any number. And the reason we've done that is because now we have as an absolute fact that 1 commutes with every number, and we're going to use that in our general proof of commutativity. So let's move on to that now. So let's start our general proof of commutativity. Again, we're going to think of A as a fixed number, and we're going to say if we happen to find a number that commutes with k, we're going to show that the next number commutes with k. So let's see what happens if we try to add k plus 1 to A. So instead of me just rhyming off all of the steps here, I want to try and show you the motivation for why we take such steps. So the reason I'm going to take my first step here is because I know that A plus k is equal to k plus A, and it wouldn't be an inductive proof if I didn't use this fact somewhere down here. So I know I'm going to have to appeal to the fact that A plus k is equal to k plus A. So let's look for a way we can do that. So I know that A and k are in here in the right order, but at the moment this is fixed as a k plus 1. It isn't a k, it's a k plus 1. But I do know that addition is associative, so let's use that. Okay, so by associativity, A plus k plus 1 is the same as A plus k plus 1. And now I can use the fact that k commutes with A. So let's go ahead and use that. Okay, now at this stage, we want to remind ourselves what we're actually trying to do. In the end, all we want is to have swapped A and k plus 1 around. In fact, let me write that down. So the actual goal here is to write k plus 1 plus A. And sometimes when we're writing a proof by induction, it's easy to start from the goal and then do your manipulations to try and get to what you've currently got, because it's just about marrying these two up. Let's just carry on with what we've got here. So we've got k plus A plus 1. Basically all we need to do is swap the 1 and the A around. and we do know that 1 commutes with everything, and we do know that we've got associativity. I'd encourage you to pause the video here and see if you can finish off this proof, but I'm going to go ahead now. So by associativity, this is simply k plus a plus 1, and we know that 1 commutes with everything, so we can freely swap these around. And now by associativity, we can rearrange these brackets, which is exactly what we set out to prove. So we have shown for any general number a, if a number commutes with a, then the next number commutes with a. All that remains to be shown is that 1 commutes with a. But it does. We've proved that 1 commutes with everything. So our induction is already finished. And since this is a stronger result than 1 commutativity, I'm just going to go ahead and replace it up here. So, we've talked about those properties of addition, and let's be honest, we've had a good time, but like the ideal date night, the fun doesn't stop here. We've defined addition, but the natural next question to ask might be, what about multiplication? Well, let's go ahead and define that. And now that I've written that down, just to clarify, I am not saying that every date should end with multiplication. So we're going to do this the way we thought about addition. We started defining addition by what happened to the first numbers. So what about if I take a general number n and multiply it by 0? Well, intuition tells us that the answer is 0, because if I have 0 lots of n, then that's just nothing at all. So let's define it in that way. And thinking about the next number, 1, what happens when I multiply by 1? Well, again, intuition tells us that if I have 1 lot of n, then the answer should be n. So again, we're just going to define it in that way. Okay, now here's the tricky part. What about the future multiplications? Well, let's think about defining n times 2. Well, I know how to do n times 1, and to get to the next multiple of n, I just add n. Great, and now I know how to times by 2, so what is n times 3? Well, if I do n times 2 and then add n, that's like having 3 n's. And n times 4, now that I know how to do n times 3, is going to be n times 3 plus n. So very much like the definition of addition, we're going to define it recursively. N times k will be do the previous multiplication, so multiply by the number before k, and then add n to finish off the multiplication. So let's just write that down. Sorry, I've ended up squeezing things over here. No matter how many times I use a board, I never ever learn. Make use of all the real estate you've got over here. There's tons of space. So we've got n times k, so timesing by a general number k, is n times the predecessor of k, and then add n. So just think about that intuitively. N times a number, do the previous multiplication, and then catch up to it by adding a copy of n. So that should kind of make sense in our heads. But once again, we want to avoid using this predecessor because we haven't defined that. And we're going to use the exact same trick as last time. Let's frame things. Instead of thinking about k, let's think about k plus 1. See? I told you I never learn. So just again convince yourself that this definition is the same as this one. So if I want to times by a number, say 12, in this definition I set k equal to 12, and it will tell me how to do it. Here I would set k equal to 11, and this k plus 1 will become 12, so I get the exact same thing in both cases. But the advantage of this way is that I know what k plus 1 is. It's the successor of k, and I know what the predecessor of k plus 1 is. It's just k, so let's go ahead and simplify it. So just one note about this definition is I'm using addition as part of the definition, and I'm allowed to do that because we've already established addition as a concept. So mathematics is this cumulative thing where we define one thing and then we build on top of it. And speaking of building bricks, I've got a multiplication brick here, which I'm very excited to show you and very relieved. Not because it's fascinating, but because this board has been balanced so precariously the entire time, and I'm hoping this will make it more stable. Now, like we did with addition, what I'd like to do is just go through an example of multiplication so you can see this definition in action. So 7 multiplied by 3. Let me show you how this definition works. So what it's saying is if I take 7 and multiply it by 3, well, the definition of 3 is as the successor of 2. Now, what the definition of multiplication says is if you have one number times the successor of another number, then it's the product of that first and second number, and then we add a copy of the first number. And much like the addition definition, it's all about reducing the problem into simpler cases. So I've got 7 times 3, I don't know what that is, but I've reduced it into 7 times 2, and I just have to add 7 to the result. But I know how to add 7 because we've discussed addition at length. So 7 times 2 is what I need to work out. So let's do that. Well, this is 7 times 2, but the successor of 1 is equal to 2. So I can rewrite this as 7 times the successor of 1, and then just add 7 at the end. Okay, now, again, the definition of multiplication says if I have one number times the successor of the second number, it's the product of the first and second number, and then add the first number to the result. So let's go ahead and do that. This is 7 times the successor of 1, and I still need to add 7 to the result. That's that plus 7 here. And now look, we've reduced the problem from 7 times 3 to 7 times 2, and just add 7 on the end, to 7 times 1, and just add 7 on the end, and just add 7 on the end. But now 7 times 1 I know how to do. It's defined to be 7 itself. So 7 times 1 is just 7. So the problem is now just 7 plus 7 plus 7. I don't think I need quite so many brackets, but there we are. So now at this stage we would apply our addition definition over and over and over, and eventually the problem would boil down to 21. But like what I said about the sets, you know, the number sets, you know, the number set 3, do mathematicians permanently think of numbers as sets? Not really, they're just encoding the numbers. These definitions encode how to do arithmetic on those sets. But once we've got them set up and established and we've proved that they work the way that we want them to, we can just go ahead and use our current understanding of addition. And my understanding of addition is so vast that I know how to do 7 plus 7. I know it sounds crazy, but it's true. And then I can add 7 to that and get 21. So now multiplication works exactly the way we expect, so I can use my own understanding of multiplication, which does in fact encompass the knowledge. I don't want to brag here, but I know what 7 times 3 is. We've just shown that it applies to our understanding of sets. From that mathematical foundation of building those number sets, we have now defined addition and multiplication, and we are in the middle of proving that it all works the way we expect. But what about the properties of multiplication? With addition, we proved that it was associative and commutative. Can we do the same with multiplication? Yes, we can. But before we do that, we showed that addition played nice. I want to show you a law that shows that addition and multiplication actually play nice with each other. Let's talk about distributivity. So you might have seen distributivity before, sometimes known as the distributive law. Sometimes we call this in the UK expanding brackets. You might know it as multiplying out brackets. It's the idea that if I have a sum multiplied by something, that's the same as if I carry out the multiplication separately and then take the sum. And I've called it right distributivity because this is multiplying on the right by C. I haven't yet shown that I can just swap these round. That would be left distributivity because I haven't yet shown that multiplication is commutative. So once again, we're going to do this by induction. And again, think of A and B as fixed numbers. And we're going to say if we have a number k that distributes on the right, then we will show that that means the next number must distribute on the right. So the idea is if k distributes, then k plus 1 distributes. So let's times a plus b by k plus 1 and see what happens. So again, think back to what I said earlier about how we construct these proofs. At some point, we're going to need to use the fact that a plus b all times k is a times k plus b times k. We're also going to need to apply our definition of multiplication. How do we apply that definition? So we know how to times by 0, we know how to times by 1, and we know how to times by the successor of something. So let's rewrite this in terms of the successor of k. Okay, and we'll apply the definition of multiplication. So we're multiplying by the successor of k, so that means we times by k itself, and then we add a copy of a plus b. Okay, and now here we know we're on the right track because we know that a plus b all times by k is equal to this sum over here. So let's go ahead and use it. And this is where we can really enjoy the fact that we've done a lot of the legwork with addition. So we've basically got 4 things added together here, and we can basically swap them around and add them in any order we like, because we know that addition is associative and commutative. So let's go ahead and put the a's together and the b's together. And the reason we've done that is because we want to apply the definition of multiplication. We know that anything of the form a times something plus a, so this thing here, this is going to be a times the successor of k. It's kind of applying the definition of multiplication in reverse. Here we did something times the successor of k, is that something times k plus itself. Here we're doing that in reverse. We've got a times k plus a, that's a times the successor of k. And similarly here, we've got b times k plus b, that's b times the successor of k. And don't lose sight of what we're actually trying to do. We're trying to show that k plus 1 distributes across a and b, but the successor of k is k plus 1, and you'll see that we're actually done here. And we're done with this step because we've shown a plus b times k plus 1 is a times k plus 1 plus b times k plus 1. So we've shown that if k distributes across a plus b, then the next number k plus 1 distributes across a plus b. All we need to show now is that 1 is distributive with a plus b, but that will actually prove to be pretty trivial. A plus b times 1 is just a plus b. That's how we defined multiplying by 1. But now a is the same thing as a times 1, and b is the same thing as b times 1. So 1 does indeed act distributively across a plus b. So 1 distributes, and we showed that if a number distributes, then the next number distributes. So that means 2 distributes, and that means 3 distributes, and so on. By induction, right distributivity holds true. Now, as for whether multiplication is associative and commutative, it's true, and you can prove that multiplication has these nice properties. I'm going to leave that as an exercise to the viewer because the proofs are by induction and very similar to the proofs for addition. But go ahead and try it, it'll be a good exercise. And with those properties of associativity and commutativity for multiplication, which I'm going to trust you've done your homework and proved, then we can actually improve the law of distributivity. So look at this, we've got right distributivity, but we can actually go ahead and swap these two terms around. So this here is the same as this here by commutativity. And now I can do the same thing with the terms over there. So a times c is actually the same as c times a. And again, b times c is the same as c times b. So this on the right is equal to that. So we do indeed have equality there. So c times a plus b is the same as c times a plus c times b. So that's left distributivity. And since we have left distributivity and right distributivity, we just go ahead and call it distributivity. Okay, so we've got addition and multiplication. They've got a bunch of nice properties and they play nicely together. The next obvious question is, what about subtraction? Well, that's easy. So let's look at a subtraction. Let's look at something like 5 subtract 2. We just define that to be the number which, when added to 2, gives us 5. Because we've defined addition all well and good, so let's just define subtraction in this way. So the obvious answer is 3. So we go ahead and define subtraction that way. 5 subtract 2 is defined to be 3. Easy. Let's do another one. So let's do something like 3 subtract 7. So we just define that as the number which, when added to 7, gives us 3. And we find the number which... Negatives. We haven't even defined what a negative number is yet. And I hate to end on a negative, but that will have to wait until next time. Nah, don't give me that look. Be rational about it. I want to keep things real in this video and not make things too complex. Now, before we add Jern allow me to adorn this video with an addendum. A massive thank you to all my patrons. I hope you've been enjoying the updates and the bloopers. My next teaching job is part-time, so your support is going to be crucial to me going forward if I'm to keep making videos, which I really want to. If you'd like to support me, you'll find my Patreon link down below. If you're not able to, don't worry about it. Subscribe and share the video. That will help me out as well. This video's Patreon question was submitted by Pat. Thank you so much for your support, who asks, how big is infinity? Well, allow me to answer your question with another question. Which one? I think it's fairly common knowledge at this stage that some infinities are larger than other infinities when we're discussing the cardinalities of sets. So for example, the cardinality, the size of the set of the natural numbers, is strictly less than the set of real numbers, even though both sets are infinitely large. Cantor's diagonal argument proves that, and I think a lot of YouTubers have already covered that, and I don't really want to make videos about topics that I feel are already covered ground unless I can find a way to add my own flavor to them. But we also use it in different ways. So in calculus, we use infinity as arbitrarily large. So as x tends towards infinity, it just means to become greater without bound. Or in the Poincare upper half plane representation of hyperbolic geometry, infinity is used as its own kind of separate element. Maybe sometime in the future I will make a video on infinity, but until then, this has been another proof under another roof, and I bid you adieu.